All right, in this video I've called it 1-6b because I kind of split these topics up. We're going to talk about linear and angular speed or velocity. I've heard both of them. When you get into calculus, there's an actual difference between speed and velocity, also in physics. And so on this video, we're going to define and find angular displacement. We're going to find angular speed, and we're also going to find linear speed. In a circle, if I put a point on the outside, on the outside of a circle, and that point moved over time, that would be the linear speed, or how fast an object moves around a circular path. So that's what linear speed is. Angular speed says as the linear speed is going, the angle around here, the central angle, is also changing. And so the angular speed is how fast the angle is changing. So I put several diagrams on here because each one of them said it just a slightly different way. This delta theta means that it's changing. The delta S means that that linear is changing with respect to time. So many times you will see linear and angular speed in terms of revolutions per second or radians per minute or something like that, because it's always in terms of a measurement over time. So we're going to do some examples now so that you'll see them. I'd say most of these problems have to do with changing the units, like changing from radians to degrees or degrees to radians, inches to feet to, whatever. And so that's what we're going to look at right now. Angular displacement is best described by looking at this diagram. This is a very crude diagram that I drew here. This is a circle with a center at O and a point P on the circle. As P moves, this angle also changes. So the change in this angle is the angular displacement. So P moves from P to P prime. And so you can see that. So it says a wheel makes 1.25 rotations about the axis. Find the angular displacement in radians of a point on the wheel. So I have, there are a couple of different ways to do this, but 1.25 rotations, we're still talking about radians always. One rotation would be 2 pi. So that's one way to do it. Just multiply through by this, and you would end up with 5 pi over 2 radians. Another way to think of it is 1.25 revolutions times 2 pi radians in 1 revolution. And when you notice the revolutions cancel, it's the same basic thing, but this would still be 5 pi over 2 radians. Angular velocity or angular speed is denoted with this omega. It says omega of a point moving in a circular path is the angular displacement theta of the point per unit time. So here is the formula. We have angular velocity is going to be the theta divided by time. So first example, a wheel makes 3 rotations every 30 seconds. Determine its angular velocity in radians per second. So 3 rotations, okay, and I do 2 pi every rotation, that's radians, in 30 seconds, okay, and so I'm going to, it says in radians per second, so that's what I have left here. I have 6 pi over 30, which is the same thing as pi over 5 radians per second. Right? It says when a this should say wheel, turns at the rate of 600 revolutions per minute, 1 minute, okay, what's its angular velocity in radians per second? All right, so 1 revolution is in 2 pi radians, right, because I need to get it in radians per second. And then I also have minutes here. So then I have 1 minute is 60 seconds. Okay, so the minutes cancel, the revolutions cancel. I'm left with radians per second. And so when I do 60 into 600, that's 10. 10 times 2 is 20 pi radians per second. Okay, the last one is determine the number of revolutions per minute of a wheel with an angular velocity of 20 radians per second. So I'm going 20 radians per 1 second, and I want revolutions per minute. So I'm going to change seconds to minutes. Okay, so the seconds, those are going to cancel. And now I've got to change radians to revolutions. So 2 pi radians is 1 revolution. All right, so the radians cancel. So that's going to be 120 over pi. No, 120 over 2 pi, sorry. And so that's 60 over pi, which of course you would convert to a decimal, and that's revolutions per minute. Revolutions per minute. Okay, linear velocity. If an object moves around a circle of radius r at a constant rate, its linear velocity is the distance s traveled along the circumference of the circle per unit time. So it would be the arc length in terms of time, and remember that from arc length, r, or s equals r theta, where theta is the angular displacement. All right, so we're going to determine the linear velocity of a point rotating at angular velocity omega at a distance r from the axis of revolution, given that r is 2.3 meters and angular velocity is 0.7 radians per second. All right, so that's where we're going to begin, is we're going to start with the angular velocity at 0.7 radians per second. Okay, and I'm going to multiply that by the radius, which is 2.3 meters. Okay, and then I need to have linear velocity, so I'm going to get rid of the radians. And so to do that, I'm going to set up a proportion here. I've got 2 pi radians over 2 pi. So basically, these are going to cancel. What I need is just the radians to cancel. So I just did a form of 1. So that does this. This also cancels, and I'm going to be multiplying 0.7 times 2.3, and I'm going to get 1.61, and then I'm left with meters per second. Okay, in this next example, it didn't have all the information it needed, so I added a little bit to it. We're going to determine the linear velocity of a point that is one unit from the center. The radius is 1 meter. That moves through an angle of 3.2 radians in 1 minute. And we're going to express this in centimeters per second. Okay, so I've got radians per minute. So I'm going to start off with 3.2 radians per 1 minute. And I need to convert to seconds. So I know that 1 minute is 60 seconds. So I've got the seconds figured out. Okay, the other thing I know is that the radius is in 1 meter. 1 meter. Okay, but I need centimeters. So I know that 1 meter is going to be 100 centimeters. So I'm going to go ahead and do that conversion as well. So 1 meter is 100 centimeters. Okay, so minutes, meters have canceled. Now the last thing that I need to cancel out is the radians, right? So I know that 2 pi radians, and then put the 2 pi up here because that's 1 revolution, right? And so the 2 pi cancels, the radians cancel, and when I multiply all the way through there, I should get 32 over 6 centimeters per second. Okay, we're going to have a few problems to do, additional problems to do in class. So take note of this and look at the examples. You may want to play through this one more time, and I will see you in class.